16,000 feet above Kent, late afternoon, August 15, 1940. The sun is in the west. A Spitfire Mk-1 of 65 Squadron, Royal Air Force, is climbing at 1,600 feet per minute. Behind it, about 1,000 feet higher and 3/4 of a mile back, a Messerschmitt Bf-109E4 is diving on the Spitfire's tail. The German pilot, Hauptmann Erich Stahl of Jagdgeschwader 3, has done this before. He has dropped onto British fighters out of the high sun a dozen times in the past 3 weeks. The geometry of the engagement, in his experience, always ends the same way. The Bf-109 has the speed advantage. The Bf-109 has the altitude advantage. The Bf-109 has the higher rated engine, the Daimler-Benz DB601N, a fuel-injected V12 producing 1,100 horsepower on the new 96-octane C3 fuel. The Spitfire, by everything the Luftwaffe has been told about RAF equipment, has a Rolls-Royce Merlin engine of approximately 1,000 horsepower running on 87-octane fuel that the British call blue. The Bf-109 should overtake the Spitfire in 20 seconds. The cannon and machine guns in the German fighter's wings should finish the matter in another 2. That is not what happens. The British pilot, having seen the diving Bf-109 a moment too late, slams his throttle through the gate to maximum continuous power, then past it into the emergency overboost setting that he has been told he can use for 5 minutes maximum. The Merlin engine in front of his cockpit, instead of straining and detonating, smoothly delivers an extra 25% of its rated power. The Spitfire surges forward and upward at a rate the German pilot, looking through his gun sight, does not understand. He cannot close the range. He cannot match the climb. By the time he has worked out that the British aircraft is somehow accelerating away from him at 16,000 feet, the Spitfire has rolled into a steep climbing turn that the Bf-109 cannot follow without bleeding off the energy it needs to escape. Stahl breaks away. He returns to his base at Coquelles with no kills that day. He tells his intelligence officer that evening that the Spitfires are flying faster than the briefings had said they would. He cannot explain it. Nobody in the Luftwaffe can explain it. The aircraft is the same Spitfire they had been fighting over France in May. Something has changed. What has changed is the fuel. Inside the wing tanks of that Spitfire on that August afternoon is approximately 85 gallons of greenish-tinted aviation gasoline. The color comes from a dye added by the refinery to distinguish the new fuel from the old 87-octane blue. The British called the new fuel BAM 100 for British Air Ministry 100 octane, or sometimes simply 130 grade. It looks, smells, and pours like any other gasoline. It costs the British government a little under 3 times as much per gallon as the old blue in actual production costs, although the price the Anglo-American Oil Company is charging is something else entirely. It is the most consequential fluid produced anywhere in the industrial world in the year 1940, and almost nobody outside a small circle of petroleum chemists and engine designers knows it exists. There are no books written about this fuel, there are no documentaries, there is no famous photograph of it. The men who designed the refining process that produced it are not in any popular history of the Second World War. The chemical engineers who scaled up its production from a few hundred barrels a day in 1937 to over 500,000 barrels a day by 1945 are not commemorated in any war memorial. But this fuel, sitting in the tanks of that Spitfire, and in the tanks of the Hurricanes flying alongside it, and in the tanks of every American fighter and bomber that would later cross the English Channel to bomb Germany, gave the Allied air forces a 25% power advantage over the Luftwaffe that the Luftwaffe could never match. The reason it could never match it is that the technology to produce the fuel was American, and the Germans had been refused access to it in 1937 by the man who had invented it. His name was Eugene Jules Houdry. He was a Frenchman. To understand what was happening inside that Merlin engine over Kent in August of 1940, you have to understand what octane rating actually measures, because the public conception of octane is almost entirely wrong. Octane is not a measure of how much energy is in a gallon of gasoline. Gasoline of every octane rating has approximately the same energy content per gallon, around 125,000 BTU. Octane is instead a measure of resistance to detonation. Detonation in an internal combustion engine occurs when the fuel-air mixture in the cylinder ignites prematurely before the spark plug is fired, because the mixture has been compressed and heated past its ignition threshold. The result is a sudden, uncontrolled explosion that produces enormous instantaneous pressure spikes inside the cylinder. The piston, connecting rod, crankshaft, and cylinder head all feel those pressure spikes. Severe detonation will destroy an engine within seconds. To make more horsepower from an engine without making the engine larger, designers want to compress the fuel-air mixture more tightly before igniting it. Higher compression ratios produce more efficient combustion, more torque per stroke, more horsepower per liter of displacement. The problem is that higher compression means higher temperatures inside the cylinder at the moment of ignition, and higher temperatures mean more risk of detonation. The way to extract more power from any given engine is to use a fuel that resists detonation at higher temperatures and pressures. That fuel is high-octane fuel. The numerical octane rating is a measure of how much compression the fuel can tolerate before detonating. 87-octane fuel detonates at a compression ratio of approximately 7:1. 100-octane fuel will tolerate compression ratios of 9 or 10:1. The engine designer who can put higher octane fuel into his engine can also put more boost into the supercharger, more advance into the ignition timing, and more compression into the combustion chamber. He gets more horsepower for free. The fuel is doing the work that in a lower octane engine would have required adding more displacement, more weight, more complexity. By the mid-1930s, aviation engine designers on every side of what was about to become the Second World War understood the octane problem in detail. The Rolls-Royce engineers working on the early versions of the Merlin understood it. The Daimler-Benz engineers working on the DB600 series understood it. The Pratt & Whitney and Wright engineers working on American radials understood it. They all wanted higher octane fuel. They could design engines that would extract more horsepower from any given displacement if the fuel were available. The question was whether the refining industry could supply that fuel at any meaningful scale. The answer, in 1935, was no. The thermal cracking processes that all major American and European refineries used to convert crude oil into gasoline produced fuel of approximately 72 octane rating as measured by the Standard Motor Octane Number Scale. This was adequate for automobile engines. It was inadequate for aviation engines that would, within 5 years, need at least 91 octane and ideally 100. Refiners could add tetraethyl lead, the anti-knock additive that had been developed by Thomas Midgley at General Motors in the 1920s, to boost octane by perhaps 8 or 10 points. But the lead was expensive, environmentally problematic, and there was a practical limit to how much could be added before the engine itself began to corrode. To get above 90 octane without massive lead addition, refineries needed a fundamentally different way to make gasoline. They needed catalytic cracking, and in 1935, catalytic cracking did not commercially exist. Eugene Jules Houdry was born in Domont, just north of Paris, in April 18, 1922. His father owned a small structural steel business that made architectural metalwork. Houdry studied mechanical engineering at the École des Arts et Métiers in Paris, graduated with honors, and joined his father's company. He was 22 years old when the First World War began. He served with distinction as a lieutenant in the French Tank Corps, was wounded in 1917 at the Battle of Juvincourt, was decorated with the Croix de Guerre, and returned to civilian engineering after the armistice with a profound understanding of how mechanized warfare actually worked. He had seen in the trenches the practical limits of internal combustion engines under stress. He had seen what happened when an engine failed at the wrong moment. After the war, Houdry developed an obsession with motor racing. He raced a Bugatti Type 35 in French amateur events through the 1920s. The Bugatti was a beautiful machine, but it was constrained by the quality of available gasoline. France in the 1920s produced almost no petroleum of its own. French refineries imported crude from Romania and the Middle East and processed it through thermal cracking units that produced fuel of mediocre octane rating. Houdry, racing his Bugatti, kept running into the practical limits of what the fuel would allow the engine to do. He wanted higher octane fuel. He could not get it, so he decided to make it. In 1922, Houdry teamed with a French pharmacist named E.A. Proudhon to set up a small chemistry laboratory at Beauchamp outside Paris to investigate methods of converting French lignite coal into liquid fuel. France did not have petroleum, but France had abundant lignite, the soft brown coal of northern France and Lorraine. Houdry hypothesized that lignite could be chemically processed into something resembling gasoline. With French government support, he built a pilot plant in 1929 that processed 60 tons of lignite per day. The chemistry worked, the economics did not. The lignite-to-gasoline process produced fuel that was 3 to 4 times more expensive than crude-derived gasoline. The French government, despite its strategic interest in domestic fuel sources, could not justify the cost. The pilot plant was shut down in 1930. But during the lignite work, Houdry had stumbled onto something else. He had discovered that a specific clay mineral, known to industrial chemists as fuller's earth, an aluminosilicate compound found in deposits across the American South and in parts of England, could catalyze the conversion of heavy hydrocarbons into lighter ones. The clay, when heated to around 450 degrees Celsius in contact with a stream of vaporized heavy oil, somehow rearranged the molecular structure of the oil. The long, heavy hydrocarbon chains broke apart and reformed into shorter, lighter chains. Some of those shorter chains were exactly the molecules that constituted high-octane gasoline. The yield was not large in his first experiments, perhaps a few % of the input oil converted to high-grade fuel, but the quality was extraordinary. The fuel coming out of his catalyst beds had an octane rating substantially higher than anything thermal cracking could produce. The catalyst, however, had a problem. After a few hours of operation, the clay surface became coated with a layer of carbon residue, a coke deposit that progressively poisoned the reaction. Houdry's first experiments at scale produced beautiful fuel for a brief period, and then nothing at all, as the catalyst saturated and stopped working. Every other chemist who had attempted catalytic cracking before Houdry had hit the same wall and abandoned the work. The catalyst would not last. Houdry's contribution, the engineering breakthrough that would change the war, was figuring out how to regenerate the catalyst. He realized that if the coke-laden clay was removed from the reactor and exposed to a controlled stream of hot air, the carbon would burn off cleanly and the clay's catalytic activity would be fully restored. The whole process could then be cycled. Hot oil flowed across fresh catalyst, producing high-octane gasoline. Catalyst became fouled, was switched out of the reactor, was regenerated in a separate vessel, and was switched back. With 3 or 4 reactor vessels operating in parallel, 1 or 2 could always be in production while others were being regenerated. The cycle could continue indefinitely. The process could run as a continuous industrial operation rather than a brief laboratory curiosity. This was the Houdry process, and Houdry patented it in France in 1927. He could not commercialize it in France. The French petroleum industry, dependent on imported crude and operating on tight margins, would not invest in the expensive new reactors his process required. Houdry began looking for partners abroad. In 1930, he made contact with the Vacuum Oil Company in New Jersey, one of the descendants of the original Standard Oil after the 1911 antitrust breakup. Vacuum Oil's research engineers, looking at Houdry's data, immediately recognized what he had built. They invited him to the United States. He arrived in 1931 with his equipment, his patents, and his understanding of the process, and he set up the Houdry Process Corporation in partnership with Vacuum Oil, which had recently merged with Ciccone to become Ciccone Vacuum. The Great Depression slowed the work. Capital investment in new refining equipment was almost impossible to secure between 1931 and 1934. But by 1935, with American industrial activity beginning to recover, Houdry and his American partners were building pilot plants. The first commercial-scale Houdry catalytic cracker unit was constructed at the Saccone Vacuum Refinery at Paulsboro, New Jersey, and went into operation in April of 1936. It processed 2,000 barrels of crude oil per day. The fuel coming out of it was the highest octane gasoline that had ever been produced in commercial quantities anywhere in the world. In 1937, Sun Oil Company, which had taken notice of the Saccone vacuum work, commissioned a larger Houdry unit at its refinery in Marcus Hook, Pennsylvania. The Marcus Hook unit, which began operations in 1937, was the first full-scale commercial catalytic cracker in industrial history. It processed 12,000 barrels of crude per day. Sun Oil branded the gasoline it produced as New Blue Sunoco, marketed it heavily to automobile drivers in the northeastern United States, and sold every gallon they could make. The catalytic cracking process was producing fuel of approximately 88 to 92 octane rating from ordinary crude oil without requiring large quantities of tetraethyl lead. By 1939, Sun Oil and Saccone Vacuum together had 14 Houdry units in operation. Other American refiners were licensing the process. Standard Oil of New Jersey, which had initially been skeptical, began its own catalytic cracking research that would eventually produce the fluid catalytic cracker, a more sophisticated descendant of the Houdry process. Houdry's process attracted attention in Germany as well. By 1936 and 1937, German chemical companies, particularly IG Farben, were quietly approaching Houdry through intermediaries about licensing the technology. Germany understood more clearly than most observers that high-octane aviation fuel was going to be critical to the next war. German synthetic fuel from coal hydrogenation could produce gasoline of approximately 87 octane, which was adequate for the engines then in service, but inadequate for the high-compression engines that German designers were developing. If Germany could license the Houdry process, it could combine catalytic cracking with synthetic fuel manufacture to produce 100-octane aviation gasoline at strategic scale. The Luftwaffe would have a fuel advantage to match its growing tactical aviation force. Houdry refused. He was 38 years old, deeply French in his political orientation, a decorated veteran of the First World War, and increasingly alarmed by the political direction Germany had taken since 1933. He had personal connections to French Air Ministry officials. He had read the German engineering press. He had concluded by 1937 that any German company licensing his technology would do so on behalf of the Nazi state, and that the technology would be used to power aircraft that would, sooner or later, bomb Paris. He broke off all licensing negotiations with German firms in 1937. This single decision, which Houdry made on personal political grounds rather than commercial ones, may have been the single most consequential individual choice made by any private citizen in the years leading up to the Second World War. It denied Nazi Germany access to the only practical industrial process capable of producing 100-octane aviation fuel at scale. For the entire duration of the coming war, the Luftwaffe would be flying on synthetic fuel that topped out at approximately 87 to 96 octane, with brief excursions to higher ratings using methanol water injection or special additive formulations. The Allied air forces, drawing on the Houdry process and its American successors, would fly on aviation gasoline routinely rated at 100 octane and, by 1944, at 150 grade for emergency power applications. The gap between the two fuels would translate directly into the gap between the two air forces, and that gap had been opened irrevocably by one Frenchman's refusal to sell his patent. By early 1937, F.R. Banks, a noted British internal combustion engine specialist who'd worked on the Schneider Trophy seaplane racing engines, wrote a paper recommending that British aero engines be redesigned to use 100-octane fuel and that the RAF formally adopt the higher-grade fuel as its standard. Banks's recommendation was reviewed by the Air Ministry and rejected. The grounds for rejection were straightforward and rational. The United States was the only source of 100-octane fuel, and the United States in 1937 was a neutral country whose neutrality acts would prevent fuel exports in time of war. The RAF could not, the Air Ministry decided, build its operational doctrine around a fuel that might not be available when fighting actually began. By 1938, however, the political situation in Europe had shifted enough that the Air Ministry reconsidered. New personnel in the relevant departments were less risk-averse than their predecessors. Test cargoes of American 100-octane fuel reached Britain in late 1938. Trials were conducted at operational RAF stations. The Merlin engines, with appropriate modifications to the supercharger boost limits and ignition timing, accepted the new fuel and produced substantially more power. In December 1939, after the war had begun but before the Battle of France had erupted, the Air Officer Commanding-in-Chief of Fighter Command formally approved 100-octane fuel for use by Hurricane, Spitfire, and Defiant squadrons. The rollout remained discretionary. The Air Ministry wanted to use up existing 87-octane stocks before transitioning. The conversion began in late winter and early spring of 1940, on station, squadron by squadron, as supplies of the new fuel arrived and as engines were modified. The first tanker load of BAM-100 had been shipped from American refineries to Britain in June 1939. By March 1940, the New York Times reported that the RAF was converting Merlin engines as fast as the modifications could be made. The Anglo-American Oil Company, operating as Esso, was shipping the fuel from refineries in Baton Rouge, Louisiana, and Aruba in the Dutch West Indies on a cash-and-carry basis that the U.S. Neutrality Act permitted. Britain paid for every gallon in U.S. dollars or gold and shipped the fuel home in tankers that crossed the Atlantic under threat of German submarine attack. To take advantage of the new fuel, the Merlin engine had to be modified. The original Merlin II and Merlin III, the engines fitted to Spitfire Mark I's and Hurricane Mark I's in 1939 and early 1940, ran on 87-octane fuel with a maximum supercharger boost pressure of 6¼ pounds per square inch. The boost pressure was limited by the octane rating of the fuel because higher boost meant higher cylinder pressures, which meant higher detonation risk. With 100-octane fuel, the detonation threshold was raised substantially. Rolls-Royce engineers modified the boost control cutout to allow emergency boost pressures of 12 pounds per square inch for 5-minute periods. The supercharger was reset. The ignition timing was advanced. The spark plugs were changed. The cylinder heads in later production engines were redesigned with shrouded valves to handle the higher peak pressures. The result was a Merlin III that could produce approximately 1,230 horsepower at 12 pounds boost on 100-octane fuel, compared to approximately 1,000 horsepower at 6¼ pounds boost on 87-octane fuel. That is a 23% increase in maximum power, available on demand by the pilot through the throttle override gate. The increase was not constant. Higher altitudes diminished the effect. But at the altitudes where most of the Battle of Britain was fought, between 10,000 and 20,000 feet, the power gain was real and immediate. A Spitfire Mark I with 100 octane could climb 500 to 1,000 feet per minute faster than a Spitfire Mark I with 87 octane. It could fly 25 to 34 miles per hour faster at the altitudes where combat actually happened. It could pull out of dives more abruptly. It could accelerate more quickly out of a turn. Every one of those small advantages, multiplied across thousands of individual combat encounters during the summer and autumn of 1940, added up to the difference between a fighter command that could hold off the Luftwaffe and one that could not. The Luftwaffe noticed the change. German pilots returning from sorties over southern England in May, June, and July of 1940 reported that the British fighters were performing better than they had performed 3 months earlier over France. The reports were initially dismissed as combat exaggeration. As the volume of reports grew, German intelligence began to investigate. In August of 1940, a Spitfire was shot down over Kent, recovered relatively intact, and examined by Luftwaffe technical specialists. The fuel in the wing tanks was greenish in color. The Germans, who had been told by their intelligence services that the British were still using 87-octane blue fuel, recognized immediately that something had changed. They analyzed the recovered gasoline. It was 100-octane fuel of American manufacture. The report went up the German chain of command. It eventually reached Hermann Göring himself. By then, however, the Battle of Britain had been underway for 2 months. The Luftwaffe had no immediate response. German refineries could not produce 100-octane fuel in any quantity. The synthetic fuel plants at Lona and elsewhere were optimized for aviation gasoline of 87-octane. To convert them to higher-octane production would require enormous capital investment, new catalysts, and time. None of these were available in the autumn of 1940. The Luftwaffe was committed to a battle it was already losing, partly because of pilot fatigue and partly because of the radar-directed interception system the British had built, but very substantially because the British fighters were faster than they should have been. The German engineers understood what had happened. They could not fix it within the time frame that mattered. Air Chief Marshal Arthur Tedder of the Royal Air Force, speaking after the Battle of Britain ended, summarized the British victory in a public statement that has become well known among military historians. He said 3 factors had decided the air battle. The first was the skill and bravery of the British and Commonwealth pilots. The second was the Rolls-Royce Merlin engine. The third was the availability of suitable fuel. The third factor is the one that the popular history has consistently underemphasized. The first factor is the one that gets the documentaries made. The second factor is the one that engine enthusiasts have written entire books about. But Tedder, who as the senior RAF commander understood the technical realities better than anyone outside Rolls-Royce, identified the fuel as one of the 3 co-equal causes of the victory. He did so because he knew that the same Merlin engine, in the same Spitfire airframe, flown by the same pilots, would not have produced the same combat outcomes if it had been running on 87-octane. The pilots and the engine and the aircraft were necessary. They were not sufficient. The sufficient condition, the one that made the necessary conditions actually work in combat, was the fuel coming out of the Hudry units at Marcus Hook and the catalytic crackers at Baton Rouge and the Esso refineries scattered across the American East Coast and the Caribbean. What happened after 1940 was, even by the standards of American industrial mobilization during the Second World War, extraordinary. The Hudry process had been operating at commercial scale since 1937. Its capacity in 1940 was approximately 40,000 barrels per day across all licensed refineries. Within 5 years, that capacity grew by more than a factor of 12. By 1945, American refineries were producing over 514,000 barrels per day of 100-octane aviation gasoline, the largest scale-up of any specialty chemical product in industrial history. The expansion was driven by the technical extension of Hudry's original work. Warren K. Lewis and Edwin R. Gilliland of the Massachusetts Institute of Technology, working as consultants to Standard Oil of New Jersey, solved the regeneration problem in a more elegant way than Hudry's batch process. They developed the fluid catalytic cracker, in which the catalyst itself circulated continuously between a reactor vessel and a regenerator vessel, with hot oil flowing through the reactor and hot air flowing through the regenerator. The fluid catalytic cracker was substantially more efficient than the original Hudry batch units. It became, after 1942, the dominant refining technology for aviation fuel production in the United States. By 1942, Standard Oil of New Jersey had its first fluid catalytic cracker operating at Baton Rouge. By 1945, dozens of fluid catalytic crackers were in production across American refineries. The combined output of Hudry fixed-bed units, fluid catalytic crackers, and ancillary alkylation units that produced specialty high-octane blending components gave the United States a fuel production capacity that no other country on Earth could approach. Every gallon of that fuel went into Allied aircraft engines that produced more horsepower per liter of displacement than any equivalent German engine could match. By 1944, the standard American aviation grade had moved beyond 100 octane to 145 and even 150 grade for combat boost applications. The Allison V1710 in the P-38 Lightning, the Pratt & Whitney R2800 in the P-47 Thunderbolt, the Packard-built Merlin in the P-51 Mustang, all of them were running on fuel that the Luftwaffe could not match and producing horsepower figures that German engines could not approach. The R2800 Double Wasp deserves a specific mention because its combat record over Germany and the Pacific demonstrated, more clearly than any other engine, what the fuel was actually doing. The R2800 was designed in the late 1930s to deliver 1,800 horsepower from a 46-liter, 18-cylinder twin-row radial. With 100-octane fuel, it could be tuned to deliver 2,000 horsepower comfortably. With 130 grade and water methanol injection, it could deliver 2,400 horsepower for short periods, the war emergency power setting that fighter pilots used during combat. With 150 grade fuel, available in limited quantities from late 1944, the R2800 could be pushed to 2,800 horsepower for brief intervals. That is more than 55% above its original rated power. The increase was achieved without any major redesign of the engine itself. It was achieved by burning fuel that resisted detonation at compression ratios and manifold pressures that the original 1939 design had not been intended to handle. The German equivalent radial, the BMW 801, displaced 42 liters in 14 cylinders. It produced approximately 1,700 horsepower at its standard rating and could be boosted to perhaps 2,000 horsepower for short periods with special procedures. The R2800, burning American fuel, produced 800 horsepower more than the BMW 801 in equivalent operational conditions. That difference, 800 horsepower per fighter aircraft, multiplied across thousands of P-47s flying combat missions over Germany in 1944 and 1945, translates into operational advantages that no amount of Luftwaffe pilot skill could overcome. The Rolls-Royce Merlin, in its various wartime evolutions, told a similar story. The Merlin III of 1940 produced approximately 1,000 horsepower on 87 octane and 1,230 horsepower on 100 octane with emergency boost. The Merlin 61, introduced in late 1941 with a two-stage, two-speed supercharger, produced 1,565 horsepower on 100 grade. The Merlin 66, used in late-war Spitfires, produced 1,720 horsepower on 150 grade. The Packard-built version of the Merlin, manufactured in Detroit under license from Rolls-Royce, was the engine that powered the P-51 Mustang and gave that aircraft the range to escort American bombers from England all the way to Berlin and back. By 1944, the Packard Merlin V1650-9 was producing 2,218 horsepower on 150 grade fuel with water injection. The original 1936 Merlin had produced 1,000 horsepower. 8 years later, the same basic engine architecture was producing more than twice that power, almost entirely because of the fuel. The German Daimler-Benz DB605, a comparable engine in design and displacement to the Merlin, peaked at approximately 1,750 horsepower in its late-war versions with methanol water injection. The Allied engines, in their equivalent late-war configurations, were producing 600 to 800 horsepower more from comparable displacements. The German engines were not technically inferior. They were every bit as well designed and well built as the British and American engines. The German engines simply could not be tuned to extract the higher power outputs that the Allied engines achieved because the German fuel did not permit it. The bottleneck was the gasoline. What of Houdry himself? After his refusal to license his process to German firms in 1937, he had continued working on improvements to the catalytic cracking process at his American laboratories in Linwood, Pennsylvania, and at the Sun Oil facility at Marcus Hook. When France fell to the Germans in June of 1940, Houdry was devastated. He had lived in the United States since 1930, but he remained, in his own self-conception, a Frenchman. He could not return to France. He could not enlist in the French armed forces, which no longer existed in the way they had existed before May of 1940. What he could do was organize. In the autumn of 1940, Houdry helped to organize an American-based committee called France Forever, dedicated to supporting the Free French movement of General Charles de Gaulle in its effort to continue fighting Nazi Germany. Houdry became one of the committee's most active leaders, and in 1942 he was elected its president. He used his connections in the American oil industry to raise funds. He spoke at public events. He met with American government officials. He worked, through every diplomatic and informal channel available to him, to ensure that American military and political support flowed to the Free French rather than to the collaborationist Vichy regime under Marshal Philippe Pétain. The Vichy government noticed. On May 3, 1941, the Vichy regime formally declared that Eugène Jules Houdry had lost his French citizenship for collaboration with the enemy. The man whose refining process was, at that moment, being shipped from American refineries to fuel the Royal Air Force in its defense of Britain was officially no longer a French citizen. The irony was complete. Houdry took it in stride. He became an American citizen on his own application in 1942. He continued to lead France Forever throughout the war. He continued to consult on refining matters with American oil companies and with the U.S. Army Air Forces. The numbers, when assembled in one place, tell the story with unmistakable clarity. American production of 100-octane aviation gasoline grew from approximately 40,000 barrels per day in 1940 to over 514,000 barrels per day in 1945. Total wartime production of high-grade aviation fuel from American refineries reached over 2 billion barrels. By contrast, German synthetic fuel production, which peaked at 124,000 barrels per day in early 1944 across all grades of fuel combined, included only modest quantities of aviation gasoline above 87 octane. The German aviation fuel grades, when measured against the American grades by equivalent rating methods, fell consistently below American grades by approximately 10 to 15 octane numbers. Across the entire span of the war, the cumulative power advantage Allied aircraft engines extracted from this fuel disparity is difficult to overstate. Every combat sortie flown by every Allied fighter and bomber in every theater of the war was flown with a fuel advantage over the equivalent Luftwaffe aircraft. The advantage was not always decisive. Allied aircraft were sometimes shot down by Luftwaffe fighters operating at substantial fuel disadvantage. But across the millions of sorties and the millions of engine hours that constituted the air war as a whole, the fuel advantage was the structural condition under which everything else happened. The pilots flew, the engines turned, the bombs were dropped, the fighters intercepted, and inside every cylinder of every engine in every aircraft, the catalytically cracked 100-octane gasoline burned with a uniformity and a detonation resistance that the German aviation fuels could not approach. The combustion process inside Allied engines was, very simply, better because the fuel was better. After the war ended, Houdry continued his work in catalysis. By the early 1950s, with the war over and the strategic urgency around aviation fuel adduced, he turned his attention to a problem that had not yet become broadly recognized: air pollution from automobile exhaust. Los Angeles in the late 1940s and early 1950s had begun developing the smog conditions that would later become emblematic of mid-century American urban environmental decline. Houdry, applying his expertise in catalysis to the new problem, hypothesized that catalytic converters fitted to automobile exhaust systems could oxidize hydrocarbons and carbon monoxide before they reached the atmosphere. He founded a company called Oxy Catalyst Incorporated, based in Wayne, Pennsylvania, to develop catalytic converter technology for automobile manufacturers. The technology worked. The problem was that the tetraethyl lead in commercial gasoline poisoned every catalyst Houdry developed. Until lead was eliminated from automobile fuel, the catalytic converter could not be commercially viable. Houdry pushed for unleaded gasoline. He did not live to see it. Unleaded gasoline did not become mandatory in the United States until the 1970s, more than a decade after Houdry's death. But when it finally came, the catalytic converter that he had patented in the 1950s became the standard pollution control device on every automobile sold in the United States. Every modern automobile in the world, every Toyota, every Volkswagen, every Ford, every Chevrolet, carries a catalytic converter that traces its engineering lineage directly to Eugene Houdry's work in the 1950s. The same man whose catalytic cracking had powered Allied victory in the Second World War had also, in his second act, designed the technology that would clean up automobile exhaust for the next 60 years. Houdry died in Upper Darby, Pennsylvania on July 18, 1962, at the age of 70. He had been awarded the Légion d'honneur by the French government after the war, when Vichy's revocation of his citizenship was reversed. He had been awarded numerous honorary degrees and chemical engineering medals. He was a member of the American Chemical Society and the Society of Chemical Industry, but he was not famous. He was not on any popular history of the Second World War. The Houdry Process Corporation was eventually absorbed by larger chemical firms, and the Houdry name disappeared from the industrial nomenclature. The Marcus Hook refinery, where his first commercial plant had operated, was designated a National Historic Chemical Landmark by the American Chemical Society in 1996. Most of the people who drive past Marcus Hook on Interstate 95 today have no idea what was once made there or why it mattered.
In a war decided by what worked, the fuel arrived in time. It was a liquid. It came in tankers across the Atlantic. It came in pipelines from refineries on the Gulf Coast. It came in tank cars across the American Midwest. It came eventually in jerrycans and drumlots delivered to airfields all over England and France and Belgium and Italy and the Philippines and Okinawa. Every gallon of it had been processed through the catalytic cracking technology that one Frenchman, who had served in the trenches of the First World War and raced a Bugatti in the 1920s, had developed in his laboratory at Beauchamp and brought to the United States in 1931. Every gallon of it was fuel that the German Luftwaffe could not match in either quality or quantity because Eugene Houdry had refused to license his process to German firms in 1937. The Spitfire over Kent in August of 1940 escaped from a Bf-109 it should not have escaped from because the fuel in its tanks was better than the fuel that German engineers had assumed. The P-51 Mustang flying escort to bombers over Berlin in 1944 produced 800 more horsepower than its German opponents because the fuel in its tanks was better than the fuel German engineers had been able to produce. The P-47 Thunderbolt diving on a Focke-Wulf over St. Lo in 1944 carried with it into the engagement an extra 500 horsepower of war emergency boost that the Focke-Wulf could not match. None of those German pilots understood at the moment of contact what they were fighting against. They thought they were fighting better airplanes or better pilots or better tactics. They were fighting, in fact, a refining process developed by a Frenchman, scaled up by American oil companies, and delivered to Allied air forces in such quantities that no operational counter was ever possible. In a war fought between industries, the fuel was the industry. The Germans had built their Luftwaffe on the assumption that their pilots and their engines and their tactics would carry them through. They were wrong in the end, because the fuel that was supposed to power those engines was not what they thought it was. The Americans had access to a refining technology that produced fuel of a quality the Germans could not match, in quantities the Germans could not approach. The result was that Allied engines across the whole air war produced approximately 25% more power than their German equivalents at any given moment of combat. The pilots flying behind those engines could climb faster, dive faster, accelerate faster, and outturn the Luftwaffe with a margin that none of the German aces ever quite understood and none of the German engineers could ever quite eliminate. The reason was the gasoline. It came from refineries in places German bombs could not reach. It was made by a process a Frenchman had refused to sell to the Reich. It was burned by the million-gallon day in Allied engines that produced the horsepower that won the air war. It was, in the end, the war. In a war decided by what worked was the liquid in the tank. 25% more power, a fuel the Germans could not produce, a process they could not steal, a man they had tried to buy. The man had said no in 1937. The Spitfires were flying faster than they should have been in August of 1940. The Luftwaffe never figured out why until it was already over. By then, the fuel had already done its work.